In my earlier video, I had discussed about inner product and properties of inner product with example. I had seen inner product of vector space is just assignment of numbers to every pair of vectors which has certain properties. These properties I have seen in my earlier video. In inner product, if UVW with 3 vector in vector space, it will satisfy inner product V with itself is equal to 0 if and only if the vector is equal to 0. Second, inner product V with itself always greater than equal to 0 for all V. Third, inner product UV equal to inner product VU conjugate. And fourth, inner product U plus V comma W always equal to inner product UW plus inner product VW. Okay? And for any scalar, inner product U comma CV equal to C times UV. Then this pair is an inner product and this space V is a inner product space. I have seen in my earlier video this part elaborately. There exist other properties of inner product. Inner product U comma CV. By property of symmetry, we can write it as CV comma U and then pull out this C from this inner product by the property of 5. Then this would be C times inner product VU. Are you getting? And inner product U comma V1 plus V2 by the property of symmetry, we can write it as inner product V1 plus V2 comma U. And this is actually similar to inner product V1 comma U plus inner product V2 comma U. This is also properties of inner product. This property also will be included for inner product. And I had seen in my earlier video I have discussed inner product space has a geometric property. Here if you choose vector, then vector has a length, has a distance and has an angle. And this angle is denoted as inner product. And today I will see the notion of norm, which actually indicate notion of length of vector. What is the actual idea of norm of a vector space? Actual idea of norm is, if we consider the Euclidean vector x in Rn, then we all of us know the standard inner product in Euclidean vector is such type inner product x comma y equal to summation I equal to 1 to n xi yi. Length of this vector would be such type inner product x with itself, and this is actually summation I equal to 1 to n xi square. Then this is actually notation of norm, which denoted as such type. Norm of x is defined as such type. Norm of x equal to square root of, just from this line, square root of inner product x with itself. This is actual idea of length of x. Our next discussion would be distance of two vector. Distance is such type, if we consider two vectors x and y in Rn, then distance, which is denoted as norm of x minus y, this is actually would be summation I equal to 1 to n xi minus yi whole square. This is actually the length of difference between two vectors, and this is the idea of metric space, which I will discuss in my next video. Today's topic is norm on a vector space. The notion norm on a vector space. The definition is a norm on a vector space V is a function, and this is the notion of norm, which is defined from the vector space V to R. That codomain is real number because norm means just length. So always would be just scalar. So this is the real number. And here the x maps to norm of x, who is satisfying the following condition. Condition 1, norm of x always greater than equal to 0 for all x belongs to V. Because length of vector always would be positive. It would be negative, no sense. Otherwise, norm of x equal to 0 if and only if the vector x equal to 0. Third condition, norm of cx equal to c times norm x, where for all c belongs to R and for all x belongs to the vector space V. And fourth condition, the triangle inequality, norm of x plus y less than equal to always norm x plus norm y, where for all x y belongs to the vector space V. This is actually the triangle inequality. This is the norm x, this is norm y, and this is norm of x plus y. Norm of by triangle inequality, this is always true. Norm of x plus y less than equal to norm x plus norm y. Different type of inner product on the vector space R. Since inner product is generalization of dot product, I had seen in my earlier video on Rn, inner product is defined as x1 y1 plus x2 y2 up to xn yn. Okay? But there exists also different type of inner product on Rn. Consider other inner product. Here they denote as xy inner product xy prime, which is equal to 2 times x1 y1 up to xn yn. Obviously, this is also inner product, and this will satisfy all condition of inner product. Actually, likewise basis, we all of us know in Rn there exists one standard basis, but otherwise standard basis there exists infinitely basis of Rn. Similarly, this inner product is standard inner product in Rn. There exist many other inner product of Rn. See another example of inner product. At first, check it on self, this inner product. This very easy type question. It will satisfy all condition of inner products. Now I will see one different type of inner product, and to consider this inner product in better way, at first I will consider just R2. Here obvious, since I have considered the vector space R2, so inner product is defined as inner product from R2 cross R2 to R, and here inner product u comma v is equal to x1 y1 minus x1 y2 plus x2 y1 plus 2 x2 y2, where the vector u equal to x1 x2 and vector v equal to y1 y2 in R2. Here we can write this expression as a matrix. Notice here row vector x1 x2 and here y1 y2. Here the matrix is such type. Just notice the coefficient. The coefficient of x1 y1 is 1, and the coefficient of x1 y2 is minus 1, x2 y1 is minus 1, and x2 y2 is 2. Notice, if you multiply first x1 x2 with this matrix A, consider this is A matrix, then this would be x1 minus x2 comma minus x1 plus 2x2 times the column vector y1 y2, then this would be x1 y1 minus x2 y1 minus y2 x1 plus 2 x2 y2. and notice this expression and this expression as similar. We're getting how we can write this expression as a matrix from OA. Now I will check. This will satisfy all condition of inner product. It satisfies the condition of symmetry property. At first consider the VU vector, then this would be, here this is notation inner product of UV will satisfy the condition of symmetry. So inner product VU would be, just change, here would be Y1, Y2, then this matrix, and here would be X1, X2. Okay, this is actually transpose, and since this matrix is symmetric matrix, that means A transpose always equal to A. So actually inner product VU is similar to inner product UV. Okay, and other property also will be satisfied. If we want to find U plus W comma V, that means actually we have to find the distributive under addition, and we all of us know matrix addition is always distributive, so always is satisfied this distributive property. And when we multiply inner product with constant term C, then obviously from this matrix C would be pull out, that means this would be C times UV. Now I will check the condition of positivity. Product U with itself is greater than 0, because inner product U with itself means x1 square minus x1 x2 plus x2 x1 plus 2x2 square, and this is actually similar to x1 minus x2 whole square plus x2 square, and this is the square term, so obviously this would be greater than equal to 0, and U with itself is equal to 0 when x1 x2 is 0. That means obviously imply U equal to 0. That means it will satisfy all condition of inner product. Are you getting? OL. That means this is an example of inner product in R2 space. Similar to before, if you consider inner product from R2 cross R2 to R such that inner product U comma V equal to UA V transpose, which is defined as 2U1 V1 plus U2 V2. This is similar to before. Always be example of inner product of R2. Just check quickly. Inner product U with V, which is actually UAV transpose. If we apply again transpose, then this would be by the property of transpose, V transpose transpose, A transpose, U transpose. Since A is a symmetric matrix, so A transpose equal to A. Just put the value. Then V transpose transpose A times U transpose is equal to VA U transpose. And VA U transpose means inner product V with U. That means condition of symmetry has satisfied here. Let's check the condition of linearity. Inner product U plus V with W. This is equal to U plus VA W transpose. So this is equal to obviously UA W transpose plus VA W transpose. And we all of us know UA W transpose means inner product U with W And VAW transpose means inner product V with W. Next condition, inner product CU with V, which is equal to CU times A times V transpose. And by the property of scalar, we can write it as easily C times UA V transpose. That means this is equal to C times inner product UV. Okay. Next condition is positivity. Inner product U with itself, which is equal to UA U transpose. This is equal to actually U1 U2. This is the matrix, and transpose means here U1 U2, which is equal to 2 U1 square plus U2 square. And since this is square term, so this part is obviously greater than 0. And when inner product U with itself is equal to 0, that means 2 U1 square plus U2 square equal to 0. And this implies obviously this part equal to 0 when U1 comma U2 equal to 0 0. Are you getting? OL. And this function actually is not same as dot product of R2. Are you getting? That means this is different type of inner product of R2. Actually, in Rn or R2, there exists many inner product. This type of inner product actually the standard inner product of R2 or Rn. I will leave out one exercise for all my viewers. If AB diagonal matrix, any diagonal matrix of n cross n with the condition ai greater than 0 for each I belongs to 1 to up to n, then the function inner product which is map Rn cross Rn to R, where R be any scalar number, is defined as inner product U comma V equal to UA V transpose. Obviously this is always inner product of Rn. Check it on self. Similar to before, you will easily check this is an inner product. But if any AII means any diagonal entries is negative or 0, then the function does not define an inner product. As for example, show that the following function is not inner product. Inner product U with V, which is equal to U1 V1 minus 2 U2 V2 plus U3 V3. Here notice, if we write this term as UA V transpose, then obviously this would be diagonal matrix, but here A22 is negative. So it may be break the condition of inner product. Let's see. Consider V equal to the vector 1 2 1. Then inner product V with itself is equal to, just put this vector, this component in this expression, then this would be 1 minus 2 times 2 times 2 plus 1 times 1, and this is equal to minus 6, which is obviously less than 0. Means it breaks the condition of positivity. So this example not be inner product. Are you getting? OL. And from this idea, I will get one new type of matrix, positive definite matrix. Positive definite matrix is, consider AB symmetric n cross n matrix with real entries. Then A is positive definite if VA V transpose greater than 0 for all non-zero V belongs to Rn. And VA V transpose equal to 0 only if V equal to 0. Are you getting? What is the idea of positive definite matrix? OL. Next idea is about positive semi-definite matrix. A matrix is positive semi-definite if VA V transpose greater than equal to 0 for all non-zero V belongs to Rn. So, there exists a nice theorem. If A is positive n cross n matrix, then the function which is defined as inner product from Rn cross Rn to R, which is defined as inner product U with V is similar to UA V transpose. Obviously, this is always inner product of Rn. And conversely, if there exists a inner product of Rn which is defined as inner product from Rn cross Rn to R, then there exists a positive definite matrix A such that inner product U with V equal to UA V transpose, where for all UV belongs to Rn. Now let's verify any positive definite matrix be inner product. This is very easy type proof. For competitive exam, this type of proof is very important. So, just see the proof. First condition is linearity. Here, I have combined these two conditions, multiplication and addition. Inner product AU plus BW comma V equal to, by definition, AU plus BW times A times V transpose, which is equal to AU AV transpose plus BW AV transpose. Okay? And this is AU AV transpose means, since inner product UV defined as UAV transpose, that means this is A times inner product UV plus B times inner product WV. Okay? That means condition of linearity has satisfied here. And this will satisfy the property of symmetry because inner product UV equal to UAV transpose. Now apply again transpose. Then by the property of transpose, this is equal to V transpose, A transpose, U transpose. And since this is the positive definite matrix, so obviously A is symmetry matrix. Therefore A transpose equal to A and V transpose to the power transpose of always equal to V, and this is actual inner product VU. Okay, that means symmetry property has satisfied here. This obviously satisfies the positive definite property because this matrix is positive definite matrix. So inner product U with itself, which is equal to U transpose, obviously this value greater than 0 when U not equal to 0. This is definition of positive definite matrix. And inner product U with itself equal to 0, that means U transpose equal to 0. And this part equal to 0, but the definition of positive definite only when U equal to 0. That means all condition of inner product has satisfied here. Are you getting why any positive definite matrix be inner product? I will highly recommend you please see this topic with pay attention. Okay? Well, because this topic is very important for any competitive exam. Now let's consider one matrix. Here the column vector is 2 minus 1 0 minus 1 2 minus 1 0 minus 1 2. Let's verify, is this matrix is positive definite? Now we have to calculate V transpose MV. Now consider the vector V equal to ABC. Then V transpose MV would be, just put the value. Then this would be 2a square minus 2ab plus 2b square minus 2b plus 2c square at first. Now simplify this part. A square plus, this would be a square plus a square minus 2ab, b square plus b square minus 2b, and 2c square means c square plus c square. And this value would be a minus b whole square, and this value would be b minus c whole square. This is c square and this is a square. And notice this part is the sum of square. Therefore, obviously this is non-negative. Okay? And 0 when the value a, b, c equal to 0. That means since V transpose MV is greater than 0 for all non-zero vector V, therefore this matrix is positive definite. Are you getting? Well, I will stop here. In my next video, I will discuss this topic elaborately, but I will highly recommend you, please see today's video with pay attention, because this part is more important for any competitive exam and also higher study also.